Okay, so this will be just a really brief introduction to finite element software. The intention is to get you far enough down the road that you can model your little bridge, apply loads, get member forces, and choose some members. When we do the structural analysis class, we'll get far more involved in this, but for now, this will give you kind of your first exposure to this. Okay, so here's an example of how this can be used. So this structure here is a large mining structure. It has some pretty heavy equipment on this level, about 100 or 300,000 pound pieces that sit in 3 different locations. Has a bunch of screens up top. You can kind of see them right here as well. So this finite element model was what the engineering basis of this building was. This is a pretty complex example. There are definitely more simple models and versions, and we'll see some of that in this. So what is a finite element model? It's basically discrete elements, in this case line and shell, that mathematically connect. So at each node, there's a mathematical connection between forces and displacements. And then understanding or knowing the stiffness, both material and geometric stiffness of the shells in this case and line elements, you can find all kinds of fantastic information. All right, so the general approach is outlined here. The first step is to create the nodes. So something I would recommend is before you just dive in and start tediously connecting nodes or creating nodes, is to coordinate the project in a BIM software like Revit or something similar where you can work out coordination issues rather than spending the trouble of designing or creating an entire finite element model and then having to keep 2 models running in parallel. So starting off with the nodes, in this case, I've turned on the node numbers and the geometric coordinates. The next would be to connect the nodes by right-clicking the members and connecting them. Let me pull that up, and well, I think I'll do a separate video of RAM here in a second. Anyway, so once you create the nodes, you create the members and shells, then you apply both materials and sections. In this case, for the shells, you apply a thickness and then the material. So C4-60 means 4,000 PSI concrete, 60,000 PSI rebar. All right, then figuring out the geometry or the loads from the geometry and ASC 7. I like to keep them clear rather than like merging a bunch of different loads together, say a bunch of dead loads. I rather apply them separately. That way it's easier to understand where they came from. You can imagine a model like this. The complexity just kind of begs for simplicity. All right, once we have that, we can assign our load combinations. Be thorough. The computer can't figure out which load combination will control. It just has to solve them all, and then it can say, oh, that one's the biggest. Whereas, say we were designing a floor beam, live load would control. So we'd automatically choose the live load heavy load combination, which happens to be 2 in this case, and run it by hand, but the computer isn't that smart. So we have to tell it, hey, check everything possible, and then you can take it from there. All right, once we have that, we can hit analyze. A lot of times it doesn't run at first, which is fine. It just means we have boundary conditions that need to be set up better. Here's some results. These are axial loads in this frame, and then here are some bending stresses in that foundation. All right, design checks, how close to 1 is okay. That's up to you. Probably more up to the engineer of record on the project, which may be you sooner than you expect. In this case, taking braces to 100% feels fine to me. I like to keep my columns maybe 60 to 70%, but I can also handle it when they go to 100%. So it just depends. Sometimes we have structures that are non-redundant and keeping the stresses low makes sense. Sometimes we have structures that are highly redundant and pushing things also makes sense. All right, then how do I know things are right? There's a number of ways. Experience can be one of those, hand calcs can be one of those, and then maybe doing a simpler model. So something like this that's extremely complicated, if I'm wanting to validate it, maybe I make a copy, isolate just say this little frame, get rid of everything else, apply some simple loads to it and see if it does what I expect it to do. If it does, that's a good sign that things are running properly. RAM has some nice little modules that are kind of standalone or tied to the software, so we can design beams, concrete columns, etc. You can see what's here. There's also a connection software, which, because I have that installed as standalone, it doesn't show up here. And I'll show that to you in the next video here quickly. All right, different resources. I've given you a link to a bunch of YouTube stuff that RAM's put out, which seems quite good. Inside of the RAM software, there's the manual and some examples. Those are also good depending on how you learn, whether video or just looking at the manual is your style. And then kind of more in depth on some of those playlists on YouTube that are really quite good. Okay, so that's kind of the introduction. What we'll do for this segment of class is meet in the computer lab where this software is installed. You folks can work on things. I'll mingle around class and help you out when you get stuck with things.